What is going on, guys? Welcome back. In this video today we're going to learn about the knapsack problem, and we're going to implement 3 different algorithms to solve it in Python. So let us get right into it. Alright, so we're going to learn about the knapsack problem, and we're going to implement 3 different algorithms in Python in order to solve it. Now, the knapsack problem is a classic optimization problem. It's quite straightforward and easy to understand. I'm going to explain it in a second here. However, it is NP hard, and I'm not going to explain in detail what NP hard means. It's a little bit too much for this video today, but practically speaking, it means that we don't have any algorithm that runs in polynomial time, any fast algorithm, so to say, which finds the optimal solution in all cases. So given a knapsack problem, we don't have a fast algorithm that finds the optimal solution to it, the best solution to it in all cases. Now, the knapsack problem itself is quite simple and straightforward. We have a knapsack. Let's say this is our knapsack, and this knapsack has a capacity. This could be weight allowed, or this could be space available. Let's say we have 10 units of capacity in this knapsack, or maybe let's say we have 50 units. So we have an empty knapsack with 50 slots if you want, and then we have a pool of items, and we could have 1,000 items, we could have 500 items, it doesn't matter. We have different items, and each item has a weight to it, or a capacity needed to it, and a value. So for example, I could have something like a key, and the key could have a weight of 2 units of weight. And then it could have 50 units of value, because this is a valuable key, for example. Then I could have something like a monitor, and a monitor could have, 10 units of weight and 55 units of value. And then we could have something like, a gold bar, like this, maybe. And this has a weight of, 5 and a value of 200 or something. And let's say we have 1,000 different items. The goal of the knapsack problem is to optimize now, or the optimization problem here is to optimize the content of the knapsack. So we have 50 slots, 50 capacity units, and we can use them up with the different items. So I can take the key, and then I would only have 48 capacity left and already a value of 50. So the content of my knapsack has now a value of 50 and 48 capacity left. And with 1,000 items, the idea is now, which items would I fit into my knapsack to maximize its value with the limited capacity? So I have a limited capacity of 50. Which items should I put into it to maximize the value of the content? So it's actually quite simple to understand. It's not too complicated. I think most of you guys probably understand now what the goal is, but solving it is not that easy. Now, getting to a good solution might be somewhat easy, but getting to the best solution when you have a lot of items and a lot of capacity is not very easy. And we're going to implement now in Python 3 different algorithms to find the optimal, or to find good solutions, or even the optimal solution. And we're going to start here with some items that I got from ChatGPT. So I let ChatGPT define the problem for me here. Very simple. I think these are 15, or how many? I think there are 15 items. And they all have a weight and a value to them. So you can see that these are the items that we're going to work with. Now, I'm going to say right away, this is a very small problem size. If we have 15 items, this basically means that no matter how bad the algorithm is, no matter how slow it is, we're going to find the optimal solution in less than a second, because that is really a small problem size. But the concept is the same, meaning that we don't have a fast algorithm doesn't mean that we can't solve this problem really fast. It means that the more items I add, the slower I'm going to get to a solution. So it's going to grow exponentially, or it's going to grow in a way that is problematic. So it's not fast, it's not polynomial given the input size. So with 15 items, if I add another one, the growth of the runtime is not polynomial. So it's not something to the power of a constant. It's more complicated than that. So yeah, we have the items, and then we're going to say from itertools import combinations, and we're also going to import time to measure the time that we need for the different algorithms. And the first algorithm that I want to implement here is the so-called exhaustive search, or the brute force solution, you could say. Basically going through all the combinations, trying every possible configuration, and getting the one with the highest value. That's like the brute force way. We try absolutely everything, and then we we just pick the best solution that we found. Of course, we're going to get the optimal solution because we saw all of them. We're going to define here the capacity to be equal to 50. So we have a limit of 50. And then we're going to define a function knapsack brute force. And we're going to say that we have the items and we have the capacity that we pass to this function. Now, the basic idea here is, again, to just go through all the possible combinations, try all configurations, and for those that are below the capacity, so get all the items, combine them in all the different ways, and see if they're below the capacity, and if yes, treat them as a viable solution, and then just pick the one with the best value. So we're going to say n is equal to the length of the items. How many items do we have? 15 in our case. And then we're going to say that the best value is going to be 0 by default. The empty knapsack has a value of 0. And what we're going to do then is we're going to say for, let's call this r in range, and we're going to go to n plus 1. So we're going to go for the number of items. We're going to iterate. We're going to say for the combination, in all the combinations, given the items, choosing r items. So basically what this means is we look at the 15 items, how many combinations are there to pick one of them? Obviously 15. How many are there to pick two of them? And then we get all the combination of pairs, all the item pairs, so to say, and then all the item triples and so on. So we get all the combinations for the given r, and we do that for all r's that are possible, for 1, for 0, 1, 2, 3, and so on, up until n items. So basically, we get absolutely all combinations. We get just this item, we get just this item, we get these two items, we get these two items, we get this item and this item, then we get all these items, all the possible combinations of the items. We look at them and we decide if they're viable and if they're better than the best value that we have. So we say that the total weight of the solution that we're looking at right now, of this particular combination that we're iterating over right now, we calculate the weight of the item for every item in combination. So we iterate over all the items in this particular combination that we're looking at. We look at the weight. We also look at the value, basically the same thing, but with the value for item in combination. And if the total weight is less than or equal to the capacity, so if it's a viable solution, and if the total value is better than the best value that we have, then we're going to update the best value to be equal to total value, and we're going to say that the best combination is equal to the combination. And of course, we should initialize that. Best combination is equal to none by default, and then we're going to update that. All right. And then we're going to return, of course, the best value and the best combination. So this will guaranteed find the best solution, but it does an exhaustive search. It's very, very inefficient because we go through all the possible combinations. We go through all the combinations that are even not possible, that are not viable. We calculate the weight and value for all these combinations, which of course means we're going to find the optimal solution, but we're going to do it in a very inefficient way. So I'm going to print here the knapsack brute force applied to items and capacity. And what I get is I get 270 is the best value I can get out of these items here. And the best configuration is to get this item, this item, this item, this item, and this item. And this results in a value of 270. And we can also actually print maybe we can keep track of the used capacity equal to none. Let's just go and say used capacity is equal to total weight. I want to see how much I use. And in this case, I use 219, which is not true because, of course, I want to use capacity. Yeah, 50. So 50 is the capacity that I have. So I use all of the capacity and I get a value of 270. All right, so this is the brute force solution, which is inefficient, but will always find the best solution. Now, the second algorithm will not guarantee to find the optimal solution, but it will be a heuristic, so it will find a usually decent solution, even though there's no guarantee, in a reasonable amount of time. But before we get to it, I want to analyze the runtime complexity first. For each of these algorithms, I want to analyze the runtime complexity and explain why it's inefficient. Now, for this one, think about it that way. This algorithm runs in a runtime complexity, for those of you who know what it is, which is 2 to the power, or O of 2 to the power of n. So it's exponential runtime complexity. The reason behind that is because for n items, we have for n items, we have 2 to the power of n possibilities, possible subsets, because of course each item can either be included or not included. So it has a 2 for every item. So 2 states for every item, and then we have all the combinations. In addition to that, we also have this loop here, which is in O of n. So basically, since you're multiplying that, the accurate runtime complexity would be n times 2 to the power of n. But since 2 to the power of n dominates, this is basically the same of saying O of 2 to the power of n. Again, if you don't understand runtime complexity, I recommend you watch my tutorial series or my course on algorithms and data structures. It's free on YouTube. You can watch it. There I explain what this basically means. But this is exponential runtime complexity. So it's really, really bad. You don't want to have 2 to the power of n runtime complexity. This is not good, because every new item will double the work. It will not just increase it by 1. Adding 1 additional item will double the amount of work that has to be done to find the optimal solution. All right, so let's move on with the heuristic, and the heuristic is going to be a greedy heuristic. So we're just going to go with the best item that still fits into our knapsack, with the most with the highest value item that, or actually with the highest value per weight item that fits into our knapsack, with the item that has the best ratio between how much value it gives you and the weight it uses, which is not always the optimal item to choose, because sometimes it might make sense to go with an item that has a lower ratio but leave space for more items then. So yeah. Let's go with knapsack greedy here. Again, taking items and capacity as parameters here. And what we're going to do here is we're going to sort all the items. I'm going to say items sorted is going to be equal to sorted items. And how are we going to sort this? We're going to define a lambda expression given an item x. We're going to calculate this ratio, the value divided by the weight. So which one has the best efficiency in and of itself? I'm going to reverse this to have the highest, or the largest items first. And the first item of the list will be the one with the best ratio, with the highest ratio here. And the greedy approaches always take this one if it still fits into our knapsack. So we're going to say total value equals 0, total weight equals 0, chosen items is going to be an empty list. And then I'm going to just iterate over the items. I'm going to say for item in item sorted, which of course will be the right order. I'm going to start with the best quote-unquote item first. And the only thing I want to consider is if the total weight that I already have plus the weight of this item, if that is still below or equal to the capacity, if it still fits into my knapsack. And if that's the case, then I'm going to say chosen items append item total weight plus equals item weight and total value plus equals item value. And that's basically all we do here. We just go through the items, looking at this metric, at this ratio, value to weight ratio. And what I do is I basically just say, if it fits into the knapsack, take it, otherwise move on to the next item, to the next best item, and that's it. And then I return, of course, the total value, the total weight, and, or actually no, the chosen items and the total weight. This was the correct order that we have up here. Value, items, and weight. Value, items, weight. And this will give me, if I run this print, probably, oftentimes it can also result in the optimal solution, but there's no guarantee because the greedy approach is not always the one that leads to the best solution. So if I say knapsack greedy items and capacity, let's compare that to the one that we had previously, which was the brute force. Now you can see that the greedy approach finds a solution 245 value and 44 capacity used. This is what happens when you follow the greedy approach, because it picks the ones with the highest value to weight ratio, but then of course it fails to use up all of the space. It is not the optimal solution, but of course it's a good solution or somewhat decent solution, and this is way faster. So this runs actually in n times log n time, so not quite quadratic. So the runtime complexity of this is O of n log n. And the reason for that is that what we do, of course, is we have to sort the list, and this is actually the difficult part. Sorting the list is already in n log n, so already by doing this we have the problem, because this part here runs in linear runtime. We just iterate over the items, so this part down here has a runtime complexity of O of n, but the sorting itself, even though we don't implement it ourselves, sorting in and of itself can only happen in O n log n. So yeah, that's the fastest way that you can sort. So since this again dominates this, the runtime complexity of it is this. That's the basic idea here. Because it's actually, you could say this, or I'm not sure, is it written like this or like this? I'm not sure, but basically it's irrelevant, because that's the difficult part. The sorting part is what produces or what leads to a higher runtime complexity. So that is the runtime complexity. By the way, one thing that you can do here just to get an idea of what's happening is you can count the operations, or you can count the iterations. So to see, for example, that 2 to the power of n is the runtime complexity of this, what you can do is you can just keep track of it. You can say runtime counter here, just to play around with it. Runtime counter is 0, and every time you iterate over a combination, you can increase the runtime counter by 1. Now, of course, this will not take into account this loop here, so you will not see the n times 2 to the power of n. You can also try to count them, but you can at least see that this loop here leads to or these loops here lead to a runtime complexity of 2 to the power of n, and the way you can see that is you just print it in the end. You can say runtime counter, and when I run this, you will see that this is the number I get. This is how many times I get into this loop in here, and then you can multiply this with n, or by n, or actually, was it n? I think so. But what you can see is that I can open up a calculator, and I can see 2 to the power of 15, which is my n, is exactly this number. So you can actually get a proof that this is the correct runtime complexity here for this particular loop. All right. Then finally, since we now have this heuristic that does not necessarily find the optimal solution, but it runs in n log n time, which is okay. This is even better than polynomial time. Then we have the brute force solution, which finds obviously the best solution, but it finds it in exponential time. Now we're going to look at the third algorithm, which is still not polynomial, because the problem is still NP hard, but it's better than the brute force solution, and it guarantees to find the best solution, and this is the dynamic programming approach. So we're going to create a function called knapsack dynamic, again with items and capacity as parameters. And here now we're going to initialize a matrix, a grid, so to say, of the size weight, or of the size capacity, and number of items. So we have one field, you could say, or yeah, one field for every combination of item number and capacity number. So if we have capacity 50, we have 0, 1, 2, 3, 4, 5, 6, 7, and so on, up until 50. And for 15 items, we have 0, 1, 2, 3, 4, 5, and so on. Basically, we have a grid of items and capacity. And the reason for that is because we want to store a matrix where every position in the matrix tells me what's the optimal solution up until this point. So I'm going to code a little bit, and then I'm going to explain it. I'm going to say that n is again the length of the items. And then I'm going to initialize this matrix. I'm going to call it dp. And this is going to be the following. It's going to be initialized with 0. So 0 for placeholder in range. And then we're going to say capacity plus 1 for placeholder in range. And then n plus 1. This is exactly what I said. We had this grid, n times w. You could call this n times weight or n times capacity. And the basic idea now is, I'm going to add this as a comment here. Our goal is that dp at position I for the item number and w for the capacity limit, that this basically means the best possible value. The value of this is the best possible value for weight limit w by using the first I items. That's the basic idea. I have the first I items that I'm allowed to use with a weight limit of w, and the position in the matrix, the value here, should be the best possible value, the highest value that I can get using these constraints. So basically what I'm going to do is I'm going to fill up this matrix now. I'm going to say for I in range, n plus 1. For w in range, capacity plus 1. And here now we're going to say, first of all, if I is 0 or w is 0, so if I'm allowed to use 0 items or I have a capacity limit of 0, then of course I'm going to just say that dp at this position is 0. Which I'm not sure if we even need to specify explicitly because we initialize everything as 0, but we're going to just say this is now explicitly 0. Otherwise, if the item that we're looking at now, so the new item, the next item to add to the list, if that is below the capacity limit, below w, what we're going to do is the following. So if items I minus 1, the weight of that, if that is below or equal to w, then we're going to consider it. And now what we want to do is we want to see, okay, does adding this item, considering how much weight it takes, how much capacity it takes, does adding this item to the best possible scenario with the remaining capacity, does this lead to a better score than the best score that I already have? So we're going to say that dp at the position iw, our grid at the position iw, is going to be the max of two scenarios. The first scenario is I take the value of the item that I'm considering and I add it to the best possible solution, that we already know, since we're filling up the table. We're getting higher and higher, so the previous spaces are always going to be filled up. So when I look at the table and I see, okay, what's the optimal solution using all the items before this item, so I minus 1 here, and getting the weight minus the weight that I would need for this additional item, so w minus items I minus 1 weight, is this better than what I already have here? So then the optimum that I already have here. So in other words, I know this might sound too complicated now. The basic idea is my item is below the capacity limit that I'm looking at right now. Taking the value of this item and adding it to, so this part is maybe a little bit confusing. This basically means I have a certain capacity. To add this item that I'm considering, I need to take away capacity. With the remaining capacity, using the items up until now, what's the best possible value that I can have? Adding this item now, the value of this item to it, is this whole thing better than just taking the best possible solution with I minus 1 items, or up until I minus 1 items? That's the basic idea here, and we just pick the better one. Otherwise, else, dp iw is just going to be whatever it was before. Whatever it was before using an additional item. We just leave it the same. That's the basic idea. Now, this is filling up our table. This is filling up our matrix. Now, this is why it's called dynamic programming, because we're storing information in a table. What we're going to do now is we're going to say W is equal to capacity. Chosen items is equal to an empty list. And then I'm going to say for I in range n, and I'm going to start with n, and I'm going to go down to 0 with a step size of -1. So we're going to go 15, 14, and so on, down to 0. And what I want to do now is I want to backtrack through the table, and I want to say if the best solution with I items is not the same as the best solution with I minus 1 items, then we know that the item with index I minus 1 is one that improves the score, so we take it. That's the basic idea. So we say if dp I w is not the same as dp I minus 1 w, then we know that this item is a good item, so we say chosen items append items I minus 1. And then, of course, we take away from the capacity that we have left. And we repeat the same process. So we basically backtrack the table to find, okay, given my full capacity, what's the best item, or what's the best value I can get? Which item did I add to change that? And then I go back until I have no capacity left. And then I basically have, or not until I have no capacity left, but until I have iterated through my items. And then I just say total value is equal to dp n capacity, because of course my total value will be the optimal solution. It will be the best configuration possible. It will be total value and chosen items. There you go. And maybe, I mean, yeah, it's going to be the optimal solution, so we don't have to print this again. So knapsack dynamic items capacity, and if I run this, you're going to see 270. I have the exact same items as here with a different order, but basically that's it. We have the same configuration as with the brute force solution, but the runtime complexity here is better. Why is it better? Because we basically have a pseudo-polynomial runtime complexity. To be precise, it's O of n times W, so O of number of items times capacity, which is not polynomial, because polynomial would mean polynomial in terms of the input size, which would be something like n squared, for example. But we multiply with a capacity, which is not the input size. So the input size is the number of items. This is what we're looking at, and in this case, it's not polynomial. But it is way better than exponential, definitely. So because to fill this up, we basically need to go n times w. That's where it comes from. And then the backtracking is just linear. So that's not really a big deal. But this is the complex part. Filling up the table, filling up the matrix is what takes O of n times w. Yeah, so pseudo-polynomial. Now we can actually measure the time differences. We can say start equals time.perf counter, end equals time.perf counter, and then we can just print end minus start. Now maybe we can copy paste this here and also copy paste this here, and then we can copy paste this here. And then I can run this, and you can see that the brute force solution takes this long, so 0.04 seconds. This one is the fastest. It's 1.7, but you can see E minus 5, so it's very, very fast. And this one takes 0.0002 seconds. And of course, if I increase the problem size, now I can artificially do that by just adding more items. The same items, but yeah. If I do that, you can see that this takes almost half a second. This is still extremely fast, and this is also still extremely fast. And if I go and add more and more items, you're going to see that my solution, my brute force solution takes much, much longer. I'm not even sure if this is not going to take too long now, but we can wait for a couple of seconds, and then I can delete some items maybe. But you can see it takes quite some time just because I added some items. This is what it means to have exponential runtime. It's not like you're just increasing the runtime a little bit. Now it took almost 20 seconds because it was a brute force approach. This one's super fast still, and this one also very fast still. So you can see what the difference is in runtime complexity here. So that's it for today's video. I hope you enjoyed it and hope you learned something. If so, let me know by hitting the like button and leaving a comment in the comment section down below. And of course, don't forget to subscribe to this channel and hit the notification bell to not miss a single future video for free. Other than that, thank you much for watching, see you in the next video, and bye.